So in this video, we'll derive what the pressure variation is in the atmosphere. So this is sort of a small example based on the earlier two videos where you looked at how we look at the governing equations for pressure in a static field where there is no motion. So here's an example. So we talked in class about the idea that if you are at sea level, the pressure you feel at sea level is essentially due to the weight of all the air extending out to space. The weight of that air causes a certain pressure which we call atmospheric pressure. Nominally, that's given by 1.101 bar, which is 10 to the 5 pascals. So what we want to do now is to figure out how that pressure at sea level decreases as we go higher in altitude. So we want, the question is, what is P of z greater than z sea level? So what we do, we start from our fundamental equation of force balance, which is del P plus rho g K equals 0, and we aren't worried about variation in the x and y directions. So this essentially reduces to dP dz equals minus rho g. This, to remind you, is a force balance. So we have an equation that looks at pressure variation as a function of rho. This is not very different from how in class we talked about pressure variation in water, except for water this rho was constant. So the thing to do here is to realize that as we go higher, the air is getting less and less dense, and so per meter of air there is less pressure that it would exert on the air below it. So we need to figure out a way in which the density varies with height. So ideally we would like this rho to be expressed in terms of the height, but we are not given that information. So we need to figure out some other way in which we represent density. One way is to look at an equation of state. So an equation of state for water would be rho is constant. For air, the equation of state states that the density is actually related to the pressure and temperature. Notice this is not an equation of force balance. The most common mistake that's made in such problems is to assume that this density gives us the pressure variation directly. So this is just an equation of state that describes what kind of fluid we are working with, rather than saying anything intrinsically about force balance. So I could try rewriting my density in terms of pressure and temperature. If I swapped that in, I would get dP dz is minus P over RT minus P over RT times G. And let me continue over on top. I could integrate this by saying dP over P equals minus G dz over RT. And it looks like I've just swapped one problem for the other. I now have eliminated density, but I brought in temperature. I could integrate my pressure from sea level to some unknown value. so long as I knew my temperature variation. For the simplest case, if we are now given T, if T is assumed constant, is T naught, then I could integrate this and say log P is minus GZ over R T naught, or P equals P naught e to the minus Z over RT. So the steps we followed were use force balance, understand what kind of fluid it is, and then end up with a situation where you can integrate. We'll see this over and over again. So let me rewrite that once more. If T is assumed to be a constant, let me just amplify each of these. Integral dP over P is integral from sea level to some unknown Z. So I get log P equals minus GZ over RT naught plus some constant, and I know that at 0 log P naught equals minus G times 0, and therefore that C is log P naught. I stick that back in here, I get log P over P naught. Let me further simplify that. It's actually log P minus log P naught, which we know happens to be log P over P naught, and that is minus GZ over RT naught. Now I take the exponential exponent of both of these, and I get P over P naught is e to the minus. So that is sort of the kind of problems you will encounter in quizzes and midterms as well.